Good evening, dear students. This session is dedicated to discuss model questions from topic solid mechanics for preparing ECET examination. So first question we have is, as the load on the bar increases, the deformation is increasing, decreasing, remains constant, or none of the above. So delta formula is expressed as delta is equal to PL by AE. So from here you can say delta is deformation or elongation produced, and that is proportional to P. So as P increases, delta also increases. That means with the increase in load, deformation also increases. So option A is the answer, or option 1 is the answer. Moving to next question. A bar of length L is subjected to axial load P. If the length of the bar increases, the deformation will be dash. Once again the same relation, that is delta is equal to PL by AE. So from here you can observe that delta is proportional to length. Delta is directly proportional to length. So as delta increases or as length increases, the deformation also increases. Even delta also increases. So option 2 is the answer for the second question. Moving to next question. A bar of length L is subjected to axial load P. If the cross-sectional area of the bar increases, then the deformation is dash. So one single formula, and for this formula we have derived 3 questions out of it. So that is delta from here is inversely proportional to area, a power minus 1, or delta is proportional to inversely proportional to area. So as area A increases, delta decreases. So option 2 is the answer. Moving to next question. Two bars A and B are of same length having same cross section. There are two bars A and B having same cross section area. Area is A. Both the bars is subjected to load P. Bar B is having Young's modulus or elastic constant as 2 times of A. That is, for bar B it is 2 times of A. That is, for B it will be 2 times of E, and for A it will be E. The deformation of bar B is dash. So delta is equal to PL by AE. From here delta is inversely proportional to E. So delta B by delta A is equal to Young's modulus of A by Young's modulus of B, which is equal to delta B by delta A is Young's modulus of A is E actually, and Young's modulus of B is bar B is 2 times of E. So you get delta B as equal to delta A by 2. That is, it will be lesser than that of bar A. So option 2 is the answer. Yes, that's true, because A and E are associated with defining the rigidity of the bar. So if the rigidity is increased, then the deformation is not so easier. So for this question, option 2 is the answer. Moving to next question. The product of cross-section area and Young's modulus is known as A into E is associated with axial loading. So this will be referred as axial rigidity. Same way, if the question is talking about flexurial rigidity, it will be product of E and I. So E is Young's modulus and I is second moment of area or moment of inertia. Moment of inertia of area. Okay, that is flexurial rigidity. And torsional rigidity is expressed as G into J. G is rigidity modulus and J is polar moment of inertia. Okay, so for this question, option 2 is the answer. Moving to next question. A beam of length L and cross-section area A is subjected to load P, so the elongation is Y. If the axial rigidity of the beam is halved, then elongation will be dash. So delta is equal to, it is subjected to axial loading only. Although we have named it here as beam. Okay, so beam is subjected to axial load and delta will be equal to PL by AE. Okay, so if the axial rigidity, that is AE, if it is made as AE by 2, okay, if we are reducing it by half times, then delta will be equal to, that is 2 times of PL by AE. So if the rigidity is reduced, the ability to deform is going to be increased. So for this question, option 3 is the answer. That is, deformation will be doubled as the rigidity is reduced. Option 3 is the answer. That is, this is going to become delta is equal to 2 times of Y it is. So let's say if this was Y, PL by AE, or Y is equal to PL by AE. So when we reduce this area and Young's modulus by half, then the elongation is doubled. Moving to next question. A 20 mm diameter central hole is bored out of a steel rod whose diameter is 50 mm. So this is a cylindrical rod into which a hole is being bored or hole is being cut inside it, and the length of the rod is 2 meters. The tensile strength of the rod due to this operation. So tensile strength of the rod, what happens to it? Here the cross section is decreased. Cross section of rod is decreased. Okay. So if the load is kept constant, if we are not changing the load before the hole is being drilled and after the hole that is being drilled, so the material resistance is going to decrease. Material resistance decreases under the same loading conditions, and it is going to produce more amount of deformation. So once the cross section has been decreased, the strength, tensile strength of the rod will be, once the cross section is been decreased, the tensile strength will also decrease. That is option 2 is the answer. Okay. So this is going to decrease, strength of rod decreases. Okay. So option 2 is the answer. Moving to next question. A 20 mm diameter central hole is bored out of a steel rod of 50 mm diameter, length is 2 meters. For the given load, the stress in rod will be dash. So the same question has been imposed, but earlier the parameter was strength. Earlier the parameter was strength. Okay. So strength is associated with the development of internal resistances. Okay. So internal resistance is going to decrease, or it is actually inherent property of the material, and this is going to decrease if area decreases. But here stress formula, that is stress is expressed as load by area. Load by area. So area, when it is reduced to half, definitely the stress will be doubled. Okay. So stress is going to increase. Stress will be increasing. So please remember that stress is going to define the state of material. It is going to define the state of material, and this is going to be constant. It is inherent property or inbuilt property of the material. When the material is being fabricated or manufactured or produced, this property will be taken into consideration from that time itself. But stress is dependent on loading conditions. It is dependent on loading conditions. Many of the students are likely to say the same meaning for stress and strength, although the units of both are similar, but still there is a huge difference. There is a huge difference. Okay. Strength is going to define or tell more about the material capacity to bear the load, but stress is going to tell the state of material when it is under the action of forces. I mean to say that if the material is under the action of forces, the material is behaving elastically, plastically, or is it on the point of rupturing? All these things are going to define the state of the material when it is under the action of forces. But strength is going to be constant. Strength is going to be constant. Okay. So if you want me to give a simple example for this, if one person is fighting against the three persons, his strength will be same. His strength is going to be same. It is constant. But the same person is fighting against 10 persons, his level of stress is going to increase. Earlier it was 3, it was so was the magnitude of stress, but if the same person is tackling 10 persons, then the sigma value is going to increase drastically. So strength does not change, but the stress is dependent on the loading condition. Loading condition is fighting 3 persons or 10 persons at a time. Okay, that is going to define loading condition. Okay, so I hope you got some clarification in the two terms called stress and strength. Next question, moving to next question. For an elastic material, stress is proportional to strain. Stress is proportional to strain. This is up to proportional limit. Okay. So whereas in elastic limit and proportional limits are very nearby points, but elastic limit will be a little bit ahead of proportional limit. Okay. So option 3 is the answer. And endurance limit is associated with cyclic loading. Okay. So for this question, option 3 is the answer. Next, two bars A and B of equal lengths. Let's say there are two bars A, B. Okay. Lengths are same, but B has an area half of A. So area of B will be A by 2, A by 2, and area of A will be capital A. And Young's modulus, A has Young's modulus double that of B. Young's modulus of A is 2 times of E, and whereas for B it is straight away E only. When the load is applied to both the bars, the ratio of deformations, so delta is equal to PL by AE. From here, you can understand that delta is inversely proportional to AE. So length is constant and load is also constant for both. So delta of B by delta of A is equal to area of A into Young's modulus of A divided by area of B into Young's modulus of B. So this is equal to delta B by delta A is equal to area of A is A only, and Young's modulus of A is 2 times of E. Area of B is A by 2, and Young's modulus of B is E only. So if you if you calculate this, so 2 will go on the top, this will be 4. So delta B is equal to delta A, or delta A into 4, because area has been reduced of B and Young's modulus is also reduced. So it is obvious that B will have, the tendency of B to deform will be more. The tendency of B to deform will be more. Okay. Ratio of deformations between A and B, that is delta A by delta B, which is equal to 1 by 4. So remember that if the area and Young's modulus, if this is reduced, deformation is easier, or it will be more under the simple load or under the same load. Okay. So for this question, option 1 is the answer. So these were few questions or sample questions from solid mechanics for those who are preparing ECET examination. Like this, we will continue our discussion in the upcoming days. Thank you, prepare well, and all the best for your exam.